Today on How It's Made. CCD Semiconductors. Airline meals. Paper cups. And trumpets. A CCD semiconductor is the image sensor in a digital camera or camcorder. When you snap the shutter or press record, you expose the CCD to patterns of light. It captures them electronically by converting them into millions of electrical charges. The camera's processor then reads these charges and translates them into pictures or movies. CCDs, or charge-coupled devices, are made of silicon, the main element in sand. What's special about silicon? When light hits it, you get electrons. Production begins with a round silicon wafer 6 inches in diameter and about as thick as a shirt cardboard. It goes into a steam oven for 3 to 4 hours. The intense heat, along with oxygen and hydrogen gases in the steam, create a glass-like layer on the wafer. This insulates the silicon against the miniature electrical circuitry that will be built on top of it. But first, the wafer is covered in conductive material. This layer measures less than a micron. A human hair is 100 times thicker. Next, a robot applies a 1-micron thick layer of photosensitive resin, which will undergo a chemical reaction when exposed to light. A technician places a mask over the wafer. The pattern on this mask is the schematic for part of the circuitry. When you take a picture, you expose the silicon wafer to light, and that generates electrons. The circuitry carries those electrons to the camera's processor, which reads the charges and translates them into an image. This machine exposes the masked wafer to ultraviolet light. The resin underneath the circuitry pattern remains intact, protecting the conductive layer beneath it. The resin on the areas not masked by the circuitry pattern needs to be removed. Chemicals are sprayed on. This dissolves the resin, exposing the conductive layer underneath. Technicians repeat this entire process with anywhere from 13 to 30 masks until they've built up the full circuitry pattern on the wafer. Next, technicians submerge the wafer in acid, which eats away the uncovered conductive layer. So now, the only conductive material left on the wafer is the actual circuitry. Next step, a thorough rinsing in tap water to remove the residue. Then a rinse with purified water to remove any impurities left by the tap water. Throughout production, contamination is a concern. A single speck of dust can ruin an entire wafer. To protect and insulate the circuitry, the wafer is coated in liquid glass, then baked for 2 hours until the glass hardens. The wafer surface is divided into 25 million tiny square cells called pixels. When you take a photo, each pixel records the light intensity of a minute portion of the scene, generating an electrical charge. A filter on the CCD translates each pixel charge into color. The company makes this filter with 3 pigment powders: red, green, and blue. These 3 colors combined in varying ratios can reproduce any color. The camera's processor reads and then reconstructs the photograph scene pixel by pixel. Each finished CCD undergoes a battery of automated tests to ensure that all the circuits are functional. The machine marks faulty circuits with ink. Just one bad circuit means the entire CCD needs to be discarded. Technicians then check every CCD under a microscope, looking for scratches that might have occurred during the production process. The number of pixels on a CCD varies, depending on what type of camera it's for. This one is a 25 megapixel CCD, meaning it has 25 million pixels. This company even produces a single CCD that has 111 megapixels. So the next time you say cheese, remember that you're producing a digital photo thanks to all that painstaking work that went into the sophisticated CCD semiconductor inside your camera. When we return, creating the ultimate to-go meals for today's high flyers. In the earliest days of air travel, passengers really lived the high life. They were served multi-course meals that were actually prepared during flight. But as air travel boomed, this kind of service became impractical, and airlines turned to pre-made meals. Not all food fares well at high altitudes. That's why you don't see any soufflés at 30,000 feet. They couldn't possibly rise to the occasion. It's just one of the restrictions airline chefs need to consider when preparing a menu. Airline meals start with tons of ingredients, literally. Just one facility can turn out 45,000 meals in a single day. Of course, the cooks wash their hands very thoroughly because they don't want any germs stowed away in the meal. They cook on grills that are 5 feet long. At one end, they stir-fry vegetables, while at the other, they saute potatoes. Then, they spice it up. Airline food isn't as bland as it's reputed to be. Researchers believe that low humidity and the pressurized environment cause our taste buds to work less efficiently in an airplane, something to take into account when you're traveling by air. Recipes vary according to the route. Flights to more exotic locales will offer spicier dishes, while a domestic North American flight usually calls for more moderate seasoning. Cooks fire up different grills for the meat. They prepare food for the crew as well as the passengers. On many airlines, the pilot and co-pilot must eat different meals to minimize the risk of food-related illness compromising the flight. The cooked food will now be blast chilled in special fridges. Cooks scrub up again as they prepare to assemble the meals. They start with the food that needs to be reheated on the plane. It goes into foil containers. Smaller containers inside help control the portion sizes. Cooks must be careful not to overstuff them because that could cause messy spills later. A little sauce and a generous dab of herb butter, and you have the makings of a first-class meal. Finally, the food is covered with a vented lid. With each menu change, chefs must meet with airline representatives. They serve up sample dishes and discuss the ingredients with them. There's often a lot of negotiation before the final menu is agreed upon. Every detail about an airline meal is carefully planned, right down to the plates and bowls and how they're placed on the serving tray. It takes a bit of arranging to make everything fit. Once planners finalize the arrangements, they follow that formula in the kitchen. As with any meal, presentation counts for a lot. Of course, meals in economy class are more simple, and the planning less detailed. The food-laden trays go onto trolleys and are rolled into a big refrigerated room where they're arranged according to the flight number. They won't be here for long because every meal is made to be served that day. And all the groundwork beforehand is sure to pay off once passengers and crew are in the air. Up next, a popular product that lets us all enjoy one for the road. The paper cup was invented around the turn of the 20th century to stop the spread of disease. Today, it's an integral part of our culture. Paper cups provide a convenient and hygienic way to serve food and beverages. And the lining of watertight plastic or wax prevents any nasty leaks. And where would we be without our disposable coffee cups? Production starts with paper that has a thin plastic coating. It unrolls into a printer that's as long as a bowling lane. As the paper weaves through the machine, printing cylinders layer an image onto the paper, one color at a time. When the image is complete, a rotary die cuts the paper into what's called a flat. The dimensions of the flat vary depending on the size of the cup being made. Each flat will eventually become a paper cup. They land on a conveyor in a shingle-like lineup. A computerized system counts the flats and divvies them up into stacks of 200. The flats drop into an elevator stacker. It creates piles that workers can easily collect. They load them into another conveyor in a different part of the factory. It moves the flats in a vibrating shuffle up into the cup machine. Meanwhile, a roll of paper winds into the other side of that machine, where a die punches out bottoms for the paper cups. This leaves a long strip of scrap paper which gets sucked away for recycling. Meanwhile, the flats are relayed to a carousel. Now the paper cup takes shape. Mechanical jaws wrap each flat, and a heat gun seals the seam. And now you have a paper cup with no bottom. That crucial step comes next. Bottoms are shoved onto the cups and heat sealed in place by melting the plastic backing on the unprinted side of the paper. The cups then fall down a chute to the next operation, which will give the cups a rim and allow you to take a sip without spilling. A hot tool curls the top edge of the paper. Then, a vacuum sucks each cup into ductwork overhead. Each piece of ductwork comes from a different production line. There are big cups and small cups, all traveling to the packing department where they land in stacking tubes. A counter keeps a running tally and portions out the stacks. The stacks then slide into a curtain of plastic. Hot jaws seal the plastic wrap around the stack. And now, the cups are ready to be packed and shipped. Meanwhile, over in the testing department, this is no coffee break. Inspectors have pulled some cups off the production line to check for leaks. A mirror below reflects the bottom line. But leaks are 1 in a million, so they've made one leak deliberately for demonstration. In the case of a real leak, production is halted and inspectors follow the paper trail until they determine the problem. It takes about a minute to transform pieces of paper into a cup. Now it's time to hit the road without any leakage. When we return, a factory with something to trumpet about. The ancestor of the modern trumpet was a straight horn that could emit just a few notes. By the 15th century, instrument makers learned how to bend the horn, allowing for more notes to be produced. The invention of the valve in the mid-1800s finally allowed the trumpet to play in any key. A trumpet is made up of 5 feet of tubing. 3 valves allow air to flow through additional tubing to alter the trumpet's pitch. Trumpets are made from sheets of metal, most often brass. This factory combines different thicknesses of brass in a single instrument to attain a particular sound. Workers first lay a template on a brass sheet and trace it out. Then they cut along the score line with electric shears. This piece will become the trumpet's bell. A manually operated press forms a perfect fold down the middle. Then they notch the edges. Then they close up the bell by hammering the notched pieces onto the opposite edge. They use a rawhide mallet because anything harder would damage the brass. A brass alloy is melted along the joint. It solidifies in a metal seam that permanently bonds the edges. Next, the bell goes over a cone-shaped mandrel, where the brass is hammered until it, too, is cone-shaped. Then the bell goes onto another mandrel mounted on a lathe. Here the brass cone is refined into a more refined shape. Then the metal is filed smooth. Now for the bell's rim, called the bead. A brass rod with a notch at the end catches the edge of the bell and rolls it back into a rim. Metal workers use what's called a concave roller to round the rim's jagged edge. Then they slide a brass alloy wire into the rim pocket. This makes the bell stronger and adds weight to the edge of the flare to project the sound better. They roll the rim over even more to enclose the wire. Now they heat the rim and apply acid flux to clean the surface for soldering. Lead or silver solder ensures the wire won't rattle when the bell vibrates. After wiping off the excess flux, the bell goes back on the lathe to scrape off the excess solder. Using an abrasive sponge, workers smooth away any scratches left by the scraper. Then they remove any solder bits trapped in the rim. Now the entire bell is filled with a soapy solution. Then it's frozen at -56 degrees. When the solution is frozen, the bell goes into a bending block. The frozen solution provides counter pressure, preventing the brass from buckling inward. And because there's soap mixed in, the pliable ice doesn't shatter under the pressure. After the angle of the bend is checked with a gauge, the bell is defrosted. In the mounting department, workers assemble smaller components made of brass and nickel. Valve casings, the sliding tubes to which they connect, the slide for tuning the trumpet, the pipe that holds the mouthpiece, Then they solder on the bell. They lubricate 3 pistons and install 1 in each valve casing. These slides have to be loose enough to move, but tight enough to prevent air leaks. One slide has a finger ring for holding the trumpet. After polishing and lacquering the brass, workers test the trumpet for sound quality. This is one company that likes to blow its own horn. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at sciencechannel.com/howitsmade.